again. Today I will tell you about a recent preprint by Roberto, Giuliano, Michael, and me. My talk is about cohomological constraints on Wigner functions. We have not overcome it.
What is the problem? Can you not move forward?
Yes, thanks. People try to grow Wigner functions in different environments. So if the number of internal states of a qudit is odd, Wigner functions grow very well. But if, on the other hand, the number of internal states of a qudit is even, they somehow do not thrive. The goal of this talk is to find out what the difference between the two environments is. And we find that the difference is cohomological. Before I can present our results, I have to introduce two things: Wigner functions and cohomology. The original Wigner function was formulated for continuous variable systems. Imagine that you have one bosonic mode. Then the Wigner function gives you an expansion of operators in the so-called phase point operators. These phase point operators are symplectic Fourier transforms of the well-known displacement operators, and the phase point operators form an orthogonal basis. Displacement operators are defined in this way, and if you multiply two displacement operators with each other, then up to a phase, you sum the phase space coordinates. This continuous variable Wigner function has many useful properties, among which are the Skatonovich-Weil criteria. These are, first of all, reality and standardization of the phase point operators. Yes, Michael. They do not see this. I thought they see this from another. Yes, so we have reality and standardization, and together this means that if you look at the Wigner function of a quantum state, we obtain a quasiprobability distribution, which is the same as a probability distribution, apart from the fact that it can take on negative values. Then we furthermore have covariance with respect to displacement operators, and we have a tertiality condition, which means that the bond rule can be represented in this very simple fashion. The Wigner function is useful for different reasons. First of all, in the continuous variable case, it is important that it allows you to avoid infinite sums. Furthermore, it turns out that by using only Gaussian functions, you can already describe a huge amount of experiments. And then the negativity in this Wigner function indicates quantumness, in the sense that whenever the Wigner function has negativity, we know that the corresponding state cannot be a mixture of coherent states. And finally, it is also experimentally accessible, it is measurable. But it is also directly related to quantum computing. Hudson's theorem tells us that whenever a pure state has a non-negative Wigner function, this pure state must be a Gaussian state. And for quantum computation with a Gaussian input state, which is subjected to Gaussian transformations and the final Gaussian measurement, we know that these computations can be efficiently classically simulated. So quantum advantage is not possible. But here we are more interested in the case of qudits for quantum computation and not continuous variable systems. Let us first discuss the case of odd dimensions, where the dimension d is the number of internal states of the qudit. The most famous construction of a Wigner function for odd dimensional qudits is the construction by Gross. Remember that in the continuous case, the central object for construction were the displacement operators. Now, Gross takes the displacement operators and instead replaces them by generalized Pauli operators. These Pauli operators consists of some discretized space, Z operator with eigenstates k, and X operator which shifts these eigenstates k. And the precise definition of these Pauli operators depends on a phase convention gamma. If you multiply two generalized Pauli operators, they behave very similarly to displacement operators. Up to a phase, we can just add up their labels. And two Pauli operators commute if and only if their symplectic product of the labels vanishes. Using these Pauli generators and this multiplication rule, we obtain the Pauli group, which contains all these Pauli operators multiplied by arbitrary discretized spaces. The generalization to n qudits from one qudit is straightforward. We simply replace these labels AZ and AX by vectors, and these vectors tell you on which qudits you want to apply Z and X operators. Gross uses a particular phase convention, which is shown here, and these phase point operators are again obtained by a symplectic Fourier transform, now of the generalized Pauli operators instead of the displacement operators. So Gross-Wigner function is again an expansion of operators in some basis of some orthogonal basis of phase point operators. And it again fulfills the Stratonovich-Weil criteria, where the covariance has become a Pauli covariance now. But Gross-Wigner function has an additional covariance property, which will be very important for us, which is Clifford covariance. The Clifford group is the unitary normalizer of the Pauli group. It means that it consists of all unitary transformations which under conjugation give the Pauli group invariant. And we identify unitaries that differ only by a global phase with each other. If we do the same identification among Pauli operators, we get the set of labels of Pauli. And if we divide the Clifford group by the labels, we find that we obtain an isomorphism to the symplectic group. Now, an element of the Clifford group acts on operators by conjugation with some representing unitary. And if you look particularly on the action of the Clifford group element on a Pauli, we find that it is characterized by some phase function and a symplectic transformation. This is now how the covariance condition for Gross-Wigner function looks like. A Clifford group element acts on the Wigner function by a symplectic affine transformation on the argument of the Wigner function. The relation between Gross-Wigner function and quantum computing is very similar to the case for continuous variables. We again have a theorem that any pure state with a non-negative Wigner function, that the pure state has a non-negative Wigner function if and only if it is a stabilizer state, which means that the state can be obtained from the old zero multi-qudit state by applying a Clifford unitary. And also quantum computation with a product state with a non-negative Wigner function as input, transformations from the Clifford group and measurements in Pauli basis can be efficiently classically simulated. Yes?
So the setting, there are a few conventions that you were taking. Does the theorem depend on these conventions, or would it still be true if you change a little bit some of these conventions?
You really need to use the phase convention, which I have shown.
I understand this is because of the theorem. This is the right choice.
Yes. Now, by looking only at this theorem, one can wonder whether the problem is about the non-negative Wigner function of the input state, or maybe about the fact that we look only at Clifford unitaries, or that we allow only Pauli measurements, right? But this can be made more specific. At least for prime dimensional qudits, it is known that there exists such magic
share your screen?
I'm very sorry. At least for odd-dimensional qudits, it is known that there exist such magic states that Clifford unitaries and Pauli measurements become sufficient for quantum computational universality. This means that the theorem which I have cited before tells us that negativity in the Wigner function, in gross Wigner function, is a necessary condition for a state being a magic state. So a necessary condition for quantum advantage and quantum computation of magic states. But why is gross Wigner function the object which reflects this property? There are two important points. First, we have Clifford-covariance, which means that if a Wigner function of a state is non-negative, it remains non-negative under Clifford unitaries. And second, Pauli projectors, so projectors onto eigenspaces of Pauli operators, are represented in a non-negative way. This means that we can sample the measurement outcomes from conditional probability distributions. Note for later that Cliffords are actually optional in measurement and quantum computation with magic states if we allow the measurements to be intermediate and not only final. Now, most quantum computing hardware is actually based on qubits. So why have we started with the odd-dimensional qubit case? The reason is that the even-dimensional qubit case is more complicated. At the beginning, it looks very similar. For example, the Pauli group can be defined in almost the same manner as before. There are subtle differences, though. For example, the discretized phase here differs by a factor of 2, and the phase convention has to be adjusted accordingly. Also, the phase convention is now subject to an additional condition, which comes from the requirement that TA to the power of D shall be the identity. Then the multiplication rule is of this form. More precisely, this beta function is of this form only for commuting Pauli operators. Regarding quantum computing, there is the famous Gauss-Mann theory for qubits, which says that the quantum circuit with a pure stabilizer state as input, transformations from the Clifford group and measurements in the Pauli basis can be efficiently classically similar. So far, everything looks very similar to before. However, as soon as we try to transfer all the results from the odd-dimensional qubit case to the even-dimensional qubit case, we encounter some no-go theorems. For example, for qubits, there is no Clifford-covariant operator basis. Or recently, it has been shown that for even-dimensional qubits, there is no diagram-preserving representation of the entire stabilizer subtheory, which contains the stabilizer states, Clifford operations, Pauli measurements, which would be non-negative. What is
diagram preserving? What?
Diagram preserving means that you can look at quantum physics as a process theory, where you have state preparations, state transformations, measurements, and you can block these processes into diagrams, which describe more complex things. And the diagram preserving representation is a representation where it is where you can map all the blocks of the diagrams, and this computes with mapping all the diagram. So what we want to know is what is the specific relevant difference between the odd-dimensional and the even-dimensional case. And the answer we give to this question is in terms of cohomology. To introduce the cohomological module, we have to start with chain complexes. Chain complex consists of a sequence of modules over some ring, which are connected by boundary homomorphisms that concatenate to 0. An element of a module is called a chain. An element of the kernel of the boundary map is a cycle, and an element of the image of the boundary map is just called the boundary. Then the homology model is defined as the quotient of the kernel of the boundary map divided by the image of the boundary map. Each chain complex has an associated cochain complex. Here the modules get replaced by maps from the modules into the ring, and the co-boundary map is acts on a chain by acting with the boundary map on the argument. Then the cohomology module, which we will consider, is just the kernel of the co-boundary map divided by the image of the co-boundary map. Chain complexes can be used to represent topological objects. Let me illustrate the idea with the example of a tetrahedron. If you want to fit a chain complex to describe this, we use first the vertices of our tetrahedron to freely generate a module over this ring R. We generate C1 from the edges, C2 from the faces, and C3 from the volume of the tetrahedron. Then we have to introduce a boundary map, and this boundary map takes any of these elements, for example, a face, right, and maps it onto an alternating sum of the boundary of this face. So, for example, for this face ABC, we will have the edge AB minus the edge BC plus the edge AC. But why do we search for a cohomological answer to our question? It is not only because we can find objects that describe something useful, but it is in particular because cohomology is a language which connects many different fields, aspects of quantum computing. So, for example, it is used for parity-based proofs of contextuality. It connects contextuality, measurement-based quantum computation, and universal symmetry-protected topological phases. And it also describes Kittai surface code and 3D cluster states for fault-tolerant quantum computing. To this web of cohomology, we want to add Wigner functions for quantum computing with magic states. So, how does the cohomological picture enter the construction of Wigner functions? Recall that the precise definition of Pauli operators depends on this phase convention gamma. Now, in principle, what we can do is asking the question whether for some, we can go through all the possible variants of gamma and ask every time whether some desirable property of a Wigner function is fulfilled for this specific gamma. Instead, we can look at gamma invariant cohomology classes and transition to the much more convenient question whether a property is at all fulfilled. We will use three cohomological objects. The first one generalizes this phase function beta. To accommodate it, we define this chain complex, where C0 is just equal to ZD, and C1 is freely generated over ZD by the Pauli labels. C2 is generated by commuting tuples of Pauli labels, and C3 is generated by triples with pairwise commuting Pauli labels. If we identify elements from C2 with such faces, and the elements from C1 with the edges, and from C3 with the tetrahedrons accordingly, and then we additionally imagine that all the vertices are glued together, then the boundary map that we use becomes actually the boundary map for from simplicial topology, which I have illustrated with the example of the tetrahedron. It turns out that beta represents an element of the second cohomology group in this setting, and two instances of beta are equivalent up to the choice of phase convention if and only if they are in the same cohomology class. The second object is a generalization of this phase function. We introduced a tilted complex, chain complex, where we have removed the commutativity conditions which we had before. And now we observe that phi tilde actually depends not only on Pauli labels, but also on group elements from the Clifford group. Therefore, to accommodate the space function, we have to use a bicomplex. The chains in this bicomplex are of this form. And this bicomplex comes with two coboundary maps now. The vertical coboundary map is the same coboundary map that we had before, and the horizontal coboundary map is the usual coboundary map from group cohomology. I illustrate it here with an example. We see that it is actually quite similar to the other maps we have looked at. And an element of the Clifford group acts on a chain by a symplectic matrix acting on the argument. Again, phi tilde represents now an element of the first group cohomology module, and 2 phi tilde are equivalent up to gamma if and only if they're in the same cohomology class. It turns actually out that we do not need all the information which is contained in phi tilde. We can remove some of it. We do this by defining the group Q, the quotient of Cliffords by Pauli labels, which we have already mentioned is isomorphic to the symplectic group. Then we can introduce a map theta that takes an equivalence class from Q and assigns to it a representative from the Clifford group. If we now evaluate phi tilde only on boundaries and not on arbitrary edges, we find that the value of phi tilde does not depend on the precise choice of the group element here, but only on the equivalence class. Therefore, we can define phi covariance in this way as a function of equivalence classes and boundaries. The phi covariance represents an element again of some first group cohomology module. And of course, we again have this property that invariance of the gamma is preserved within the cohomology class. With these preparations, I am ready to present our results. Recall that for quantum computation with magic state, it was important that the Wigner function was Clifford-covariant and it represents the Pauli measurements positively. Let me start with the Clifford covariance. We are interested here only in Wigner functions that are constructed from operator bases. Recall that the action of a Clifford group element on a Pauli is characterized by such a symplectic matrix. And we call an operator basis and the associated Wigner function Clifford covariant if and only if the Clifford group element acts on a phase point operator by transforming the phase point V by such a symplectic affine transformation. Our first main result now reads that for any number of qudits, a Clifford covariant operator base exists if and only if the cohomological equivalence class of phi covariance is 0. How can we prove this? Let me sketch this in a very short way. Assume that a Clifford covariant operator basis does exist. We can expand a knot in the Pauli operators, and we observe that if we act with the Clifford group element on a knot, we can always reproduce the result by acting with a particular Pauli operator on a knot. Now we plug in this expansion into this equation, and we find this kind of constraint or equation for phase functions, including the phase function phi tilde. If we now apply this equation to a boundary, we see that phi covariance is of this form, so it is actually a coboundary. And this means immediately that the cohomological class of phi covariance vanishes. In the other direction, if we assume that the cohomological class of phi covariance is 0, we immediately can conclude that phi tilde must be linear in A, and therefore can be written as a symplectic product. Now, as an ansatz, we choose, we again look at the phase point operators which have been introduced by Gross. And we just check that with this property, they form an operator basis and transform covariantly under Clifford unitaries, independent of whether the dimensionality is odd or even. And this first theorem can be now applied to the specific case of even dimensions. We find that for even dimensional qudits, a Clifford-covariant operator basis does never exist. And this follows from the observation that the cohomology class of phi covariance is never zero. Let me again tell you the proof idea. Assume that the proof works by contradiction. So assume that the cohomology class would be zero, and assume additionally that there exists such Clifford group element G and such a phase F, such that G leaves the boundary of F invariant. Then the first assumption implies that phi tilde must be of this form. And the second assumption implies that for this particular G and F, phi tilde must evaluate to zero. However, we find such instances of G and F that fulfill the assumption, but phi tilde does not evaluate to zero. This gives us a contradiction. So, is there any chance left for quantum computation of magic states at even dimensions? Yes, of course, because as I have mentioned, Clifford transformations are not necessary. Therefore, let us look now at the positive representation of Pauli measurements. When we elaborate on that, we make more assumptions. We do not only want that the Wigner function is constructed from operator basis, but we also assume the whole set of Straton-Ridgway criteria, though we actually relax the traceability condition before we had the Wigner function here. Now we introduce a theta function such that this, in fact, instead being a condition or a requirement, becomes just a definition of theta. We say that Pauli measurements are positively we have a state with no negative Wigner function, then the post-measurement state after a Pauli measurement has also no negative Wigner function. This second condition is, of course, important only because we want to have intermediate Pauli measurements and not only final measurements. And with this, we find our next important result, which is that for any number of qudits and for Wigner functions that satisfy our assumptions of the Straton-Ridgway criteria, a Wigner function that represents Pauli measurements positively exists if and only if the cohomology class of beta vanishes. To prove this, we first implement our assumptions into an expansion of the phase point operators. So the operator basis standardization and Pauli covariance assumptions are fulfilled if and only if the phase point operators can be written in this particular form. Let us furthermore introduce this phase phi related to exponentiation of Pauli operators. Then the reality condition can be stated in this form. From here on, we have to look only at the coefficients Ca and these phases Phi of k. We also do the same with the representation of Pauli measurements. We also bring them into an explicit form. And we find just by explicit calculation that these theta representations look like this, which is a rather simple expression, and are actually always real. Note that theta is a Fourier transform of this Ca of k, which is defined over here. And this means that we can apply a discrete version of the Bochner's theorem, which we use throughout the proofs, which says that theta is non-negative if and only if this matrix is positive semi-definite. With this, we can come to the proof, and let us first assume that a Pauli positive Wigner function does exist. First, we show that then the coefficients, the expansion coefficients all have absolute value 1. and then that the CA of K can be all written in this particular form. Plugging this into the explicit form of the theta representation, we find that the theta functions become delta functions. Now imagine that we want to measure the Pauli operator TA in the state AB. We know, because this is a delta function, precisely what the measurement outcome will be. And it is defined in this form. If we sum up this relation now over a boundary, we see that beta actually is again a co-boundary, and this means that its cohomology class is 0. In the opposite direction, we know that if the cohomology class of beta is 0, we can always choose the phase convention such that beta identically vanishes. In particular, all the phases vanish from this relation. If we now again use the phase point operators, which have been introduced by Gross, we can explicitly verify that the theta representation of Pauli projectors will be non-negative, and also that Pauli projectors transform the phase point operators in a non-negative manner, which means that the Wigner positivity is preserved under Pauli measurement. We again apply this to the case of even dimensional qudits. We find that if we have 2 or more of them, of the qudits, a Wigner function that satisfies the Platonovich-Wright criterion cannot represent all Pauli measurements positively. And this is based, of course, on the observation that the cohomology class of beta does not vanish. To prove this, we introduce these operators x tilde and y tilde and construct a generalized Mermin square from them. Each of the rows and columns contains commuting operators and corresponds to a phase. This phase can be assigned a value of beta, and if the 3 operators multiply to the identity, the value of beta is 0, and if they multiply to minus identity, the value of beta is d half. Now it is possible to sum over all these phases with the correct signs, such that we obtain an overall phase with the vanishing boundary, but beta of the phase does not vanish, equals d half. And this excludes the possibility that beta, that the homology class of beta would be 0. It is necessarily non-zero. So let me summarize our results. We have found that particular properties of Wigner functions can be developed only under appropriate cohomological conditions. So first of all, Clifford-covariant operator bases exist if and only if the cohomology class of phi covariance vanishes. And second, Wigner function that satisfies the Platonovich-Wright criteria and represent Pauli measurements positively exists if and only if the cohomology class of beta vanishes. Applying this to the even-dimensional case, we find that Clifford-covariant operator bases do not exist, and for 2 or more even-dimensional qudits, a Wigner function cannot satisfy the Platonovich-Wright criteria and represent all Pauli measurements positively at the same time. These results are the content of this preprint. Thus, we have indeed added Wigner functions for quantum computation at magic states to the web of homology. But now we have to ask ourselves, what does it tell us about quantum computation in magic states and even dimension? Is there still a chance to have Wigner negativity as a precondition for quantum speed? And the answer is actually yes, if you go beyond operator bases. Examples have been provided by Hort and Campbell or by Auxendorf and colleagues. And in all these examples, the Wigner function is not only constructed from operator bases, but it is also not unique. And interestingly, if you consider non-unique Wigner functions, then there exist also completely non-negative representations of quantum computing, as has been shown by Michael and others, and I think Michael will talk about this result on Wednesday. Where can we go from here? As we have looked on, considered Wigner functions from operator bases, And here we can ask, for example, whether one can define Clifford covariance in another way using another action, different group action, whether this would give us something useful. And it would be nice, of course, to remove some of the assumptions from the Pauli positivity result. Then one can consider non-unique Wigner functions, and there it is a particularly interesting question to answer where the quantumness resides in the cases where you have no negativity. But apart from this, one can also ask whether there are interesting Wigner functions that are unique but not constructed from operator basis. And with this, I'm at the end of my talk, and I'm looking forward to your questions.
So what does that mean, a Wigner function not from an operator basis? I understood your talk. You first take an operator basis and that defines the representation of any operator and some other coefficients of Wigner functions. So, yeah, what does that mean? Only starting from operator basis.
So in principle, it is sufficient to define Wigner function that you say you have a representation of the quantum processes, and you probably also want to require that this quantum probability distribution gives you represent the quantum state. And then you can add requirements, and you can have variance requirement or yes, so the explicit construction below that was from operating basis, but you can also try to construct this. These are the requirements. How is there an object?
From kind of a high level, what makes cohomology such a natural language to describe so much phenomena?
Oh, I don't think I can answer the question. For me, it's more, I see that it describes many phenomena, so it must be natural language, but Robert, maybe you can say more about it.
I don't know, Sven, what would you say about it? Yeah, I don't know either. It comes up in all sorts of things.
I would also add that it's probably a bit of a trend thing. You know, once you realize that some new object plays an important role, and everybody looks there, oh, maybe this is related. You know, and then okay, there's a trend to find a thing to say about this. And I guess it was the same about spectral theory, quantum mechanics.
I did not say it is very convenient. So when I was introduced to the project, Ivan showed me an introductory book about cohomology, which is quite thick, and actually what we used to obtain all of these results at the first 10 pages.
Yeah, so like if you move to continuous variables, how come they resemble odd functions somehow more than even functions?
From my perspective, the connection is along the following lines. So if you take an odd qudit system and take the infinite size limit, no, if you take the qudit system, you can always take the infinite size limit and you get some kind of continuous system. But if you take the odd G system and take the continuous limit, you have some uniqueness of representation here. If you take an even G system and take the continuous limit, then you don't have this uniqueness. I think I cannot say this more formally, but I believe that this can be viewed as a reason of why the continuous space coincide with this unique limit that shares properties with the unique, but not with the non-unique.
And so, like, because of your non-uniqueness, you can choose different properties and get different good stuff, but not get some like, other good stuff where you might want.
I'm not sure. I mean, also in what dimensions you can construct different Wigner functions, but they have been constructed.
If I may throw in something into this discussion. So from a physics perspective, not from a math perspective, but from a physics perspective, what we see is that this is in a way all about Merlin's square. And you have a Mermin square in even dimensions, but you don't have a Mermin square in odd dimensions. From a physics perspective, yeah, that is the essence of the difference.
But Mermin square for like continuous variables is probably ill-defined.
No,
Like,
no, but it would not give you a contextuality. It is, you can define it.
yeah.
Good. Let's see if we have a question in the chat. No question in the chat. And if this is it for questions, so Paulina, then let's thank Paulina again.